Welcome to the Simple Science Summary of FS Physics. Today we're aiming to cut through the complexity, give you a really clear, actionable, and hopefully pretty fascinating look at a core physics concept.
Huh.
Have you ever, just watched a kid on a swing going back and forth, or maybe felt that vibration from a guitar string after you pluck it?
Yeah. Or even just the steady tick-tock of an old grandfather clock.
Exactly. Those aren't just random things. They're examples of something fundamental in physics, oscillations.
Absolutely. And understanding these kinds of movements, these rhythms, it's not just about doing well in your IEB Further Studies Physics course, although, yeah, it'll definitely help there.
Right.
It's more about seeing how these predictable cycles are just, well, everywhere. In sound waves hitting your ear, how big buildings are designed to handle wind, even in tiny electronics. Your IEB course covers a lot of cool stuff, like charged particles moving in fields. But today, yeah, we're zooming right in on oscillations.
So our mission, if you like, for this summary is pretty straightforward. We're going to unpack what oscillations actually are. Then we'll get into a really important type called Simple Harmonic Motion, SHM. You'll see that a lot.
Crucial stuff, SHM.
And finally, we'll look at how energy moves around in these systems, which is, well, quite elegant, actually. We want to give you a clear path to understanding what really matters for your studies. Okay, so let's start with the basics. Periodic motion. What is that?
At its heart, it's just any movement that repeats itself over and over again in regular time intervals.
Like a rocking chair, just back and forth, same timing. Or maybe the satellite going around the Earth.
Exactly. Predictable repetition. Now, an oscillation is a specific kind of periodic motion. It's the one that goes back and forth or up and down around some kind of central point or equilibrium.
Okay, back and forth.
Yeah, think about tangible examples. A tuning fork, when you strike it, it vibrates, oscillates really fast, and that's what makes the sound. Or a simple pendulum in a clock, swinging. That's an oscillation. An object bobbing on the end of a spring, maybe horizontally on a table. Or even the air vibrating inside an organ pipe, or, that sound a glass makes if you run a wet finger around the rim. All oscillations.
Got it. So if these things are happening rhythmically, how do we actually describe them? Like with physics terms?
Good question. We need some key vocabulary. First up is amplitude. That's simply the maximum distance the object gets from its resting place, its equilibrium position.
So for the swing, it's how high it goes at the very peak of its swing.
Precisely, before it turns around. Then there's the period. That's the time it takes to complete one full cycle.
One full cycle, so back and forth and back again.
Yeah, for the swing, it's from one side all the way to the other, and then all the way back to where it started. That whole trip is one period.
Okay, amplitude and period. What else?
Well, related to period is frequency. Frequency is just how many of those full cycles happen in 1 second. We measure it in hertz, abbreviated hertz.
Hertz.
Right.
Right, so something is vibrating at, say, 50 hertz.
It means it completes 50 full oscillations every single second. Quite fast. And then there's angular frequency. It sounds a bit more complex, but it's basically how quickly the phase changes, measured in radians per second. Think of it as relating the oscillation to circular motion. It's directly linked to frequency and period. Usually written as omega, it's 2 pi times the frequency.
Okay, brings in the circular idea.
Yeah.
And one more. You mentioned phase.
Phase difference. This one's important if you have two things oscillating at the same frequency. It tells you if they're moving together in sync or if one is sort of ahead or behind the other in its cycle. It's about their relative timing.
Right, so if they start at different points or times. Okay, that makes sense.
And these concepts, amplitude, frequency, they seem straightforward, but they have huge real-world consequences. There's a pretty famous and tragic example involving something called resonance. Have you heard about the Tacoma Narrows bridge collapse?
Vaguely, yeah. The bridge that shook itself apart.
That's the one. Back in 1940. What happened was the wind was blowing at a frequency that just happened to match the bridge's own natural frequency of vibration. It's like pushing a swing at exactly the right moment in its cycle.
So the pushes just added up.
Exactly. The wind kept adding energy at just the right time, making the oscillations bigger and bigger and bigger until the bridge was twisting so violently it just couldn't take the strain anymore and collapsed.
Wow.
It's a very stark lesson, but it shows why understanding oscillations and resonance is absolutely vital for engineers designing anything from bridges and buildings to cars and even musical instruments. You need to know how things naturally vibrate.
That really drives the point home. Okay, so maybe quickly then, what's the difference between free and forced oscillations?
Good distinction. Free oscillations are what happens when you, say, pull a swing back and just let it go. There's no continuous external push. It oscillates at its own natural frequency. Now, in the real world,
There's friction, air resistance.
right, so real free oscillations usually die down. We call that damping. But often, for understanding the basics in this course, we look at the ideal case, undamped free oscillations.
Why ignore damping? Isn't that less realistic?
It is less realistic, but by ignoring it initially, we can really focus on the core relationship between the restoring force and the motion and how the energy works without the complication of energy loss. It lets us grasp the pure essence of simple harmonic motion first.
Okay, isolate the main idea.
Exactly. Then you have forced oscillations. That's when you do apply a continuous external force, like someone actually pushing the swing repeatedly to keep it going high.
Got it. Free is let go. Forced is keep pushing.
In simple terms, yes.
All right, so building on that, let's get into this really important specific type. Simple harmonic motion, SHM. You said it was crucial.
It really is. SHM is kind of the ideal, purest form of oscillation. It happens under a specific condition. You need a linear restoring force.
Linear restoring force, break that down.
Okay. A restoring force is any force that always tries to pull or push an object back towards its stable resting point, its equilibrium position.
The middle point where it would sit still.
Precisely where the net force is zero. Now, linear means that the strength of this restoring force is directly proportional to how far you've moved the object from that equilibrium position.
So the further away it gets, the harder it pulls back.
Exactly. Double the displacement, double the restoring force, and it always points back towards the center.
And isn't this where Hooke's law comes in? For springs.
Absolutely. Hooke's law is the classic example. It says the force a spring exerts is proportional to how much you stretch or compress it from its natural length. F equals minus kx, remember?
Right, I remember seeing that. F equals minus kx. K is the spring constant.
Yep, K tells you how stiff the spring is. A bigger K means a stiffer spring, harder to stretch. And that minus sign is super important.
Why the minus?
It tells you the force is always in the opposite direction to the displacement. If you displace it to the right, positive x, the force is to the left, negative f. It's always trying to restore equilibrium. That's key for SHM.
Okay, so the force is proportional to displacement and opposite in direction. What does that mean for the motion itself?
Well, if force is proportional to displacement, F equals kx, and we know Newton's second law, F of k, then it follows that the acceleration x must also be proportional to the displacement x.
Ah, right. FMO links force and acceleration.
Exactly. So the defining equation, or condition for SHM, is that acceleration is proportional to displacement, and crucially, always in the opposite direction. So A is proportional to mass x. When the object is furthest to the right, its acceleration is maximum towards the left. When it passes through the middle equilibrium, its displacement is zero, so its acceleration is momentarily zero too.
Okay, acceleration always fighting the displacement, trying to get it back to the center.
That's the essence of it. That constant pullback is what drives the smooth, repetitive motion.
Now, you mentioned a connection to circular motion earlier. How does that fit in? This seems like straight line back and forth motion.
It does seem like that, but here's a really neat way to visualize it. Imagine you have a turntable spinning at a constant speed, and there's a ball fixed to its edge.
Okay, like a record player.
Yeah. Now shine a light from the side so the ball casts a shadow on a wall behind it. The ball itself is moving in a circle, right? Uniform circular motion.
Right.
But look at the shadow on the wall. What does it do?
It just goes back and forth along a straight line.
Exactly. The shadow moves back and forth with perfect, simple harmonic motion. It speeds up in the middle, slows down at the ends, just like our mass on a spring.
Huh. That's quite clever.
It really is. And that connection is why sine and cosine functions pop up all the time when we describe SHM mathematically. Those functions naturally describe projections of circular motion. They describe waves.
So SHM is like the one-dimensional shadow of uniform circular motion.
That's a fantastic way to put it. It gives us a powerful mathematical toolkit and a visual understanding of why the motion is so regular and smooth.
So using those sine and cosine functions, we can describe exactly where the object is at any time.
Yep. We can write down an equation for its displacement as a function of time. It'll look like a sine or cosine wave, depending on whether it starts at the equilibrium point or at maximum displacement.
And velocity, too.
Velocity as well. It also varies sinusoidally. Remember, velocity is zero at the ends, maximum displacement, and maximum speed happens as it passes through the equilibrium point.
Where potential energy is lowest and kinetic is highest. We'll get to energy soon.
Exactly. And acceleration also follows a sine-cosine pattern. It's maximum at the ends where the force is strongest and zero at equilibrium, always pointing opposite to the displacement. We can even figure out the velocity at a specific position if we know its maximum displacement and angular frequency.
Okay, so the maths lets us predict everything. What are some common systems that actually show SHM or close to it?
Well, the mass spring system is the classic textbook example. A mass sliding horizontally on a frictionless surface attached to a spring, its motion is SHM.
And its period, the time for one cycle, depends on?
It depends on two things, the mass and the spring constant K. A larger mass means it takes longer to oscillate a longer period. A stiffer spring, larger K, makes it oscillate faster a shorter period. The relationship involves a square root. Specifically, period is proportional to the square root of m over k.
So heavier objects or looser springs mean slower oscillations.
You got it.
What if the spring is hanging vertically? Gravity's involved then.
Good point. Gravity shifts the equilibrium position downwards. The spring stretches a bit just to hold the weight. But the oscillation around that new equilibrium position is still simple harmonic motion.
Oh, interesting. So gravity just changes the 0 point.
Essentially, yes. The restoring force dynamics around that new point still follow the SHM rules. This is super relevant for things like, say, car suspension. The springs support the car's weight, but they oscillate around that position to absorb bumps, giving you a smoother ride based on SHM principles.
Makes sense.
Yeah.
Any other key examples?
The simple pendulum. Think of a mass, a bob, hanging from a string. For small angles of swing, and that small angle part is important, its motion is very nearly SHM.
Small angles.
Yeah.
Like not swinging too high.
Exactly. If you keep the swing angle small, say less than 10 or 15 degrees, the restoring force is almost perfectly proportional to the displacement.
And what determines the period of a pendulum? Is it the mass again?
Surprisingly, no. For small angles, the mass of the bob doesn't affect the period. It only depends on the length of the pendulum string, L, and the acceleration due to gravity.
Just length and gravity? That seems weird.
It is a bit counterintuitive, but true. A longer pendulum takes longer to swing back and forth, and if gravity were stronger, it would swing faster. The period is proportional to the square root of L over G.
Wow. That's why grandfather clocks, with their long pendulums, keep such good time, regardless of the exact weight of the pendulum.
Precisely. As long as the length is constant, the period is incredibly stable, making them excellent timekeepers.
Okay, so we've covered the motion, the forces, the descriptions, the examples. What about the energy involved in all this back and forth?
Right. The energy perspective is really elegant. The fundamental principle here, especially in our ideal undamped SHM, is the conservation of energy.
Meaning energy isn't lost.
In the ideal case, yes. The total mechanical energy, that's the sum of kinetic and potential energy, stays constant throughout the oscillation. What happens is a continuous trade-off, a conversion between kinetic energy and potential energy.
Okay, kinetic is energy of motion, potential is stored energy. How does the trade-off work?
Think about the extremes. At the very ends of the motion, maximum displacement, the object momentarily stops, right?
Yeah, just for an instant before it turns back.
So, at that instant, its speed is zero, meaning its kinetic energy is zero. All the system's energy is stored as potential energy. For a spring, that's elastic potential energy, like in a stretched or compressed spring. For a pendulum, it's gravitational potential energy because it's at its highest point.
Okay, all potential at the ends. What about the middle?
As it swings or moves back towards the equilibrium position, it speeds up. Right at the equilibrium position, it's moving at its maximum speed.
A maximum kinetic energy there.
Exactly. And at that precise equilibrium point, the potential energy is considered zero, or at its minimum. So at the ends, it's all potential, zero kinetic. In the middle, it's all kinetic, zero potential.
And everywhere in between.
Everywhere in between, it's a mix of both. As kinetic energy increases, potential energy decreases, and vice versa. But their sum, the total mechanical energy, remains exactly the same. It's like pouring water back and forth between two glasses. The amount in each glass changes, but the total amount of water stays constant.
That's a nice analogy. So kinetic energy depends on speed, potential on position.
Right. Kinetic energy is max at the center, max speed. Potential energy depends on displacement for a spring. It's proportional to the square of the displacement, so it's max at the extremes.
So if you plotted graphs of these energies over time,
you'd see this beautiful interplay. The kinetic energy curve would look like a wave peaking in the middle. The potential energy curve would also be a wave, but shifted peaking at the ends. And if you added them together...
a flat line. Constant total energy.
A perfect flat line for the total energy. It visually confirms that energy is conserved, just changing forms constantly. It's a really fundamental and elegant aspect of SHM.
Okay, that pulls a lot together. So recapping, we've looked at the basics, periodic motion, oscillations. We dove into simple harmonic motion, the ideal case with that linear restoring force. We saw how Hooke's law fits in, the link to circular motion, and how to describe position, velocity, acceleration. We looked at springs and pendulums. And finally, this constant energy exchange. Hopefully that gives everyone a solid summary for their FS physics.
Absolutely. Getting a good grip on these SHM concepts is, well, it's foundational. It's not just for passing exams, though it's definitely key for that. It really helps you understand so many other areas of physics and how things work in the real world, from waves to circuits to quantum mechanics. Believe it or not, these ideas keep coming back.
Right, so maybe a final thought for everyone listening. Think about the next time you see a really tall building swaying slightly in the wind, designed that way to resist earthquakes. Or maybe even think about the tiny, precise vibrations inside your phone that help keep the camera image stable when you take a photo. How are those incredible feats of engineering relying on the very same principles of oscillation, restoring forces, frequency, and maybe even damping that we've been talking about today? It makes you realize this physics is everywhere, often in places you don't expect.
Yeah.
There's always more to uncover.